The next test that we are going to do is called the ratio test. Now here it says when you have a series an and you are considering the limit of an plus 1 divided by an, and if that limit is equal to L and if that is less than 1, then we can say that the series is absolutely convergent. So even though we are considering a term in the normal series without any modulus sign, the result or the conclusion of the ratio test speaks to the absolute convergence. Okay, not only just convergence, but it will directly call for the absolute convergence. Now let's do an example on this one. Let's consider this example: the series of negative 1 to the power n times n cube divided by 3 to the power n. So here this is the anth term, right? And for the ratio test we need an plus 1 divided by an, right? So this is the anth term, and how do we find the an plus 1th term? We just replace all the n terms by n plus 1, right? So here we have replaced all the n terms by n plus 1, and then we just need to get the ratio of these two terms. And remember, you should have a modulus sign also, right? So an plus 1 is this term divided by an, and that means we are multiplying the reciprocal of this term. So now here you can see this negative 1 to the power n and negative 1 to the power n plus 1 can be kind of taken to a side, and then you can distribute this modulus across these multiplications, right? And then see now, no matter what n value you have, this one will either be negative 1 or positive 1, right? But as you have a modulus, this total result will always be equal to 1, right? So actually this negative 1 to the power nth term will not play any significant role when you are taking the modulus. Okay, right? So then we can just get rid of that negative 1 term, and then we can see that the remaining part is a positive number, right? So we can even write everything without a modulus sign, because the modulus of a positive term is equal to that same number, right? And this negative effect is kind of removed because of this modulus sign. And see, here in the ratio test itself you have a modulus sign. Okay, you have to have that modulus when you are doing the calculations, right? Okay, so then an plus 1 divided by an term will ultimately be something like this, right? So you have to take the limit of this an plus 1 divided by an, right? And the limit will be like this. Okay, you can compute the limit, and then you can see that the limit is equal to 1 over 3, right? Now have a look at this one again. So here the limit is equal to 1 over 3, and we have the limit less than 1. Okay, strictly less than 1. Now here you have a strict inequality. Okay, so our limit is less than 1. Then from the ratio test it says the given series is absolutely convergent, right? That means this series is absolutely convergent. That means even this one will converge. Therefore from the theorem that we did before, since this absolutely converges, then the original series will also converge. So that's how you have to do the converge, like that's how you have to determine the convergence of the given series, right? Since this is absolutely convergent, then you have the series to be like the original series will also converges, right? This absolute nature comes from the theorem itself, okay? And if the limit, if by any chance, let's say if the limit is equal to 3, like say for instance, if we have a certain series where when you compute the limit of an plus 1 divided by n, let's say if that is equal to 3, which is greater than 1, okay? So if that is greater than 1, then we can say that the series diverges. Now this is not something to do with absolute divergence, okay? It is just divergence, right? Remember, now there can be series where it diverges when you take the absolute values, but it converges when you take the normal values. For example, this one, right? Now you have to remember these examples, okay? Now this series, no, not this one, this one, negative 1 over n, okay? So when you take the absolute values, it will be the harmonic series which diverges. But if you just consider this one from the alternating series tests, we can say that it converges. So this is an example, where the absolute series diverges but not the original one. But if the absolute series converges, then the original one will definitely converges, okay? Now here in the second sentence, it says about just converging, okay? So it does not address the absolute series, okay? So if the limit is greater than 1, or even if it is infinity, you can directly say that the original series is divergent, not the absolute case. But if it is less than 1, you can definitely say that the absolute series is going to converge, okay? Because that's how the theorem is proved, okay? And there's one more thing. Now since we are taking the absolute values, the smallest number that this limit can have is 0, right? It will never go to the negative side because we are taking the modulus, okay? Because when you are taking the modulus, we are like taking the limit of a sequence where all these terms are positive or 0. So there's no way of going, like there's no way of having a limit for this sequence which is negative, okay? Like you cannot have a negative limit for such a sequence, okay? Right. And let's have a look at this third sentence. If the limit of this an plus 1 divided by n, an is equal to 1, then it says that the ratio test is inconclusive. I'll explain that with some examples. Okay, let's consider these two series, right? Now here, this is a converging series, and we know that from those p-series tests, right? So this converges, and this one, since this is the harmonic series, it diverges, right? But let's say if we are going to apply the ratio test for these two series, let's see what will happen. So in this case, an is equal to this one, and an plus 1 is, you can compute it like that. And since you don't have any negative terms, even without the modulus sign, you will get the same thing, right? And be careful when you are dividing the terms, right? You should do it correctly. So an plus 1 divided by n means this term divided by 1 over n squared, and that is equal to that this term multiplied by the reciprocal of this one, okay? So you will get this one, right? And then when you compute the limit, you get 1, right? And here also it is the same situation for this series. An and an plus 1 are like you can obtain an and an plus 1 like this, and when you get the ratio and get the limit, you will have the answer as 1, right? Now see, this is a converging sequence and you got the limit as 1, and this is a diverging series, and this is also a converging series. I think I said a sequence, but it was wrong. This is a series. This is a converging series and we got the limit as 1, and this is a diverging series and here also we got the limit as 1. Okay, now let's see what it says in the theorem. If the answer is equal to 1, it says the ratio test is inconclusive. That is, no conclusion can be drawn about the convergence or divergence. See, if you get the answer as 1, it can either be a converging series or a diverging series. That means from the ratio test, we cannot decide anything about the convergence or the divergence of the given series. So then we will have to go for a different technique to determine its convergence or the divergence. Okay, so keep all these data in your mind. If the limit, now here you should not take the other way, right? You should not take an divided by n plus 1. Okay, then everything will go in the opposite direction. So you must take an plus 1 divided by an. Okay, right? So if this limit is less than, now we know for sure that it is greater than or equal to 0, right? That means it is not a negative number. And if that limit is less than 1, then the series converges absolutely, right? Not just convergence, it converges absolutely. And if this diverges, right? Sorry, not diverges. If the limit is greater than 1, then we know that the series will diverges, right? So if the normal series diverges, then there is no way for the absolute series to converge, because if this converge, then definitely this must converge. Okay, so if this diverge, then definitely the absolute series will also diverge. Okay, because otherwise there will be some contradictions. Okay, now take all those logical ideas into your mind properly, right? Okay, so and if the limit is equal to 1, then the ratio test, we cannot determine anything from the ratio test. These two are very good examples to illustrate that idea. Okay, and in the next video we will do the root test.